Welcome back to week 6 of Chem 330. Now, you probably all don't remember this molecule, but if you remember in the very first class, I asked you two questions. One of them is, why do you have to take this organic chemistry class? And what are some practical implications to taking an organic chemistry class? And in one of them, I showed you a video of kids drinking two different water in two different cups. One of them contained a sweetener like Splenda, and the other contained an actual sugar. And then I also showed a separate video where people talked about the key concept of chirality. Okay, chirality. I did not expect you to remember all this. That was almost 5 weeks ago, very first class. But then in the chirality video, and both the videos actually talked about chirality, but the second video actually talked about this molecule called thalidomide. Okay, thalidomide is a infamous historic compound that was developed to help women who are pregnant with morning sickness. But unfortunately, this medicine, when it was administered to patients, it was only tested on adults, especially females. Although its side effects were never considered, because many fetuses born in Germany and across the world had limb issues, limb malfunction. Some of them had other serious health issues because the side effect of thalidomide took over on the fetuses. It did not affect the women themselves, but they apparently should have done more testing on how this would have reacted on fetuses. Because the R isomer of this, this compound had two possibilities, R and S. The R was what intended for the morning sicknesses in women. The S was never intended to play a major role. However, the S had a major issue when it came to the fetuses, and that's one of the reasons why this drug was eventually banned and it's no longer in use. Okay, so it's important that almost all pharmaceuticals that we consume are racemic mixtures. Okay, what does a racemic mixture means is that every medicine that we consume would contain, some are, varying proportions of, say, 90R, 10S, or it could be 99R, 1S. It can't ever be pure, but it's always going to have one of the other, or 1R and 99S if the S was the active ingredient. I'm going to underline the active ingredient. So you're going to always have a combination of R and S. We have not quite learned what this R and S means, but this idea of studying compounds that exist in varying, they have separate optical rotation is called stereochemistry. Okay. Okay. So these are called enantiomers, which we will, again, we'll come back to all these terms and talk more details, but I do want to introduce you to the term called enantiomers. That is, if it's an R, its opposite mirror image would be an S. If it's an S, its mirror image would be an R. So if it's an R, and if its mirror image comes out to be an S, then it's an enantiomers. If it's an S, and its mirror image comes out to be an R, then that's also a enantiomers. But what if you have, there is also another possibility that is quite true out of these things. Again, I am not going to expect you to remember all this in one go, but I'm just going to give you, the other one is stereoisomers. Okay? Enantiomers and stereoisomers. The other one is, if you have a molecule that contains R and S and you take its mirror image, well, technically you should get S and R, but what if you get S and S, right? So this is called stereoisomers that, that are not enantiomers. Enantiomers are perfect mirror images. Stereoisomers does not always have to be a perfect mirror images. Okay, actually these have a specific name called diastereomers. That's what I meant to say. Diastereomers. That is, you start with a molecule that has R and S, but then its mirror image contains S and S. Then the specific kind of stereoisomers are known as diastereomers. But if you start with an R and an S, S and an R, and then say you start with an R and an S, and its mirror image turns out to be R and S. This S becomes R, this R becomes S. Then this is also a enantiomer, right? So the idea of mirror image comes in, right? So what is chirality? Or at least I'm going to cut straight to the chase. But what is chirality, and what role does it play, right? So when you have an object, okay, let's say your fingers. Again, I am not a good artist, so I'll try my best here. Okay. Okay, so this is your, okay, and then you take a mirror image of it, right? And you're gonna get like this, right? Again, I'm not doing a very good job to keep it. Okay, I think I'm gonna go back and at least do a justification too. Okay. You see, when you take a mirror image of your palm, it looks like this. So what really happens is, if you put this directly on top of each other, that you would see that the two thumbs are on the opposite side, and the two pointy fingers are on the opposite side, and the pinkies are on the opposite side. So these don't superimpose. So what is chirality is not non-superimposable mirror images. Okay, that's the idea of chirality. Okay, whether it's diastereomers or it's enantiomers, they all contain chiral carbon. So that then takes us to the idea of what is a chiral carbon. Okay, what is a chiral carbon? If a carbon contains 4 different groups, okay, I'm going to put it in generic terms here. Okay, if a carbon is attached to 4 different groups, okay, so carbon attached to 4 different groups, okay, then that is called a chiral carbon. Is called a chiral carbon. Okay, so there is a potential pitfall to the way we write things. Okay, and that is, okay, remember we talked, again, that's what the reason why I gave you all the foundation knowledge before I started this is, when we discussed about, say, if you have methane, okay, this carbon contains all hydrogens, right? Can this be a chiral carbon? No, because it contains 4 identical groups. All 4 groups must be different. Even if 2 are different, 2 are same, no, it's not chiral. Okay, so for instance, say this is chloroform, okay, that contains hydrogen, Cl, Cl, Cl. Well, it contains 2 different groups, but then it also contains 2 identical groups, so it's 3 identical groups on here, so this is not chiral. If you don't have a chiral carbon, then you don't have chirality. You gotta have first chiral carbon for chirality to even take place, right? Now keep in mind, I said a carbon attached to all single bond is sp3, and it cannot be planar. I said this earlier, and I taught you, and I even did a worksheet on this particular area, right? Why does it matter? Okay, if it is not planar, okay, let's say we have a compound called let's make up this compound. Okay, this is the compound. All right. Now, because we teach students sometimes like this to get started, they get the idea that everything is on the plane of the paper because we literally drew it like a cross. Okay, that's not true, because we just said a carbon containing all single bonds can never be planar. If it's not planar, how can it be on the piece of paper? So I picked a compound like this. So carbon, hydrogen. I'm going to write it in a form that you have not seen up until this video. Okay. What this is when you have a sp3 hybridization, we call it tetrahedral. Okay. That means that it's like a tripod. Okay. This is where your camera is, and you have two legs, and then one leg is pointing behind. What it means in this particular compound is, first, it's a chiral carbon, and when it is a chiral carbon, you indicate it with an asterisk sign, because all four groups attached to this carbon are different, right? Now, let's say I put a piece of paper behind this molecule. Okay, what this structure is telling me is this hydrogen and chlorine are kind of on parallel to the paper behind it. This fluorine is kind of coming out of the paper towards you, and this bromine is going away behind the back of the paper. All right, so if you really construct these molecules, which I will in class, I will construct and show you that it's not like a cross that it literally sits on a piece of paper. No, it's like a tripod. So a tripod can never be flat on the ground. That's the reason why you have a tripod. It sticks out of the surface, right? So these two are kind of parallel and in plane of paper. The fluorine is coming out of the paper towards you. The bromine is going out of the paper, like behind the paper, away from you, right? So this is towards you, and this is away from you. So keep in mind, away from you or away, the point here is one is coming towards you in the plane of paper, and one is going away from you in the plane of paper, right? So these are more like parallel to the paper. These two are more like perpendicular to the paper, right? With that said, right? So now we have looked at something, right? So let's look at a few examples. So what if I have a compound like this? Now in this, there are several layers of learning involved in here. And if I ask you, identify how many chiral carbons you have in this compound, you look at one carbon at a time. This carbon is attached to this whole thing as through this bond, but then it's attached to 3 hydrogens. So no, it is not chiral. Let me get a different color so I can change up. So this is not chiral. Okay, this is not the asterisk. Asterisk is what you put for a chiral carbon. Don't confuse the X mark for asterisk. This carbon is attached to, say, this hydrogen, okay, as through one bond. Through this bond, it's attached to a methyl group, and another bond, a chlorine, and on that side, it's attached to this whole thing. Yes, so this is a chiral carbon, right? This carbon, well, straight away you can tell it's attached to 2 hydrogens. Even though it's attached to 2 separate groups, different groups on either side, this is not chiral. This is, let me actually get rid of this and get a different color. I guess I'll go with the orange. Okay, so this is chiral. Okay, this is chiral. And let me get my blue again, and this is not chiral, right? Because this contains, so this compound contains 2 chiral carbons. Okay, so I will give you all some more practice problems and and so I'll give you some more practice problems in the worksheet. But what I really want to get across this video before I start a new video is, let's say I have this, okay, the one I had earlier, okay. I'm just drawing it here for convenience. It may not even be the right one, but it doesn't really matter. Okay, so I'm gonna get the mirror image of this. All right. So the mirror image would be, right? The CL would be here, right? The BR would be on the far side, right? And the fluorine would be here, and the hydrogen would be here. This doesn't change because it's kind of in the plane, but if you take a mirror image of this, the Cl gets reflected here, the fluorine gets reflected here, the bromine gets reflected there, right? So this is how you write mirror images. So to start the stereochemistry activity, I think this would be a good place for you to just understand how to identify chiral carbons and how to write mirror images of two objects, okay? So let's do one more example. Let me do probably this. Now let's do one more. You know, this is very simple concept. I mean, we haven't only barely scratched the idea of chirality, so honestly, it shouldn't be that difficult, right? So does this compound above has a chiral carbon? If so, how many? Well, this clearly has two hydrogens, so I can't. Well, first of all, I don't think you even focus on a carbon that contains double bonds. That automatically voids itself of chirality. So I'm just gonna get my blue, or actually black would work here. So this is not chiral. This is not chiral because it also is attached to a double bond. This qualifies to be looked at because it does contain all single bonds around it. So yes, this contains a hydrogen, a chlorine. But if you look at it, these groups are exactly the same on both sides, right? So this is not chiral either. So is this, so is this, okay? One of the key requirements for chirality to even exist would be that a carbon is attached to all single bonds. If it contains a double bond, right away, whatever carbon that contains a double bond is going to be automatically not chiral. So this compound contains 0 chiral carbons. Okay, let's go to this one. These two are not right away not possible because they are attached to. So this contains a hydrogen, a chlorine, a methyl, and this whole group on the side. So clearly, it contains 4 different groups. So this would be a chiral carbon. So it contains 1 chiral carbon. So I'm going to wrap this video here because I don't want to put all stereochemistry material in one single video. Then the video would become too long. So let's start practicing this idea of being able to identify chiral carbons first before we go further into learning enantiomers and diastereomers. Okay? All right. So that's good enough. I'm going to stop the video here and then we'll come back with the second video shortly. All right, so stay tuned. Bye-bye.